Okay, we're going to get started. Welcome everybody to Introduction to Material Science. If you're a mechanical engineer, this might be called Elements of Material Science. There's essentially 4 different courses that we're smashing all into one here, right? So we've got civil engineers, we've got mechanicals, we've got material students, we've got other, right? Biomedical, chemical, we've got a bunch of other people who take this class as well. The microphone's not working. They redid this room over the summer, and they got rid of our awesome big table that we did demos on, so we'll have to think of what we're going to do there, and the microphone won't work. So I will try and speak loud. If you don't hear me, please like get my attention and say speak up, and I can be louder. What's happening right now is I record every lecture, and I'll do so for the rest of this semester, and I'll post them on YouTube right after class. I really want to make this a resource for you guys, so instead of just being an hour-long video, you have to try and dig through it and find, where was that part where we talked about this equation or that? I actually put timestamps on it in the description of the video, so if you're all familiar with YouTube, you can jump right to the exact part of the lecture that you care about. If you miss class, that becomes a really easy way for you to figure out what was missed. Anyways, let's dive into some of the key parts of the syllabus, and then we'll actually start class here, right? So first off on the book, I sent everybody an email about a month ago on the book for this class. If you added the course a little bit later, you didn't get that email, but that's okay. The textbook we're using for this class is one that's written by William Callister. There's like 10 editions of this book, and it's a lot of money, but I don't see much of a difference between those editions and the older editions, right? So you can actually use, I think anywhere between the 2nd, 3rd, and 4th edition is going to be pretty close to what we're using for the official version. If you want to buy the official version, then buy the 3rd edition. It used to be the 2nd, but the textbook the store wouldn't buy it anymore. They said it's too old. So I'm trying to save you guys money. You should be able to find this book pretty cheap on Amazon or Big Words or wherever you buy books. Okay, I will be using the Canvas as the course website quite a bit in this class. That's where you're going to see homework get posted, announcement, reading things. If you have questions on homework and you can't make it to the TA hours, we would love for you to use the discussion feature on Canvas to post a question. And don't be afraid to be the first person to post a question and feel like that everyone else already understands it and gets it, because the odds are that people are just as confused as you are. And if you post a question, people will love it because they can see what the responses are. So, course website, you guys know how to find Canvas, but it's organized just like normal. Let me point out just a couple things. We'll see assignments in here. Now, within the assignments, there will be 4 categories at the most. What will be 5? There'll be labs, in-class participation, homeworks, midterms, is that everything? But if you're, say, a mechanical engineer, you're not taking a lab. So anything that I post about labs, let me just tell you now, you can ignore it. If you're in 2160 or 2070, you can ignore that, right? They don't exist to you, right? You're missing that, they're right, but everyone else, you can worry about those. So you will see announcements about it, but just realize that you can ignore those. The same with civil engineers. You guys are only here for half a semester. After that period of time, you'll still get notifications because I've wrapped all these into one course. Don't worry, you're done with the semester. You don't need to worry about future homeworks or midterms, because I get emails every year in the middle of the semester concerned civil engineers. In the files section, this is where I'm going to be posting things like additional reading, the syllabi for the course, obviously are there, but there's also things called class notes. I lecture out of OneNote, and I like OneNote because I can sort of draw on top of it. I can build in a lecture style called notes with gaps. So I put the skeleton of each class's notes in there, but I leave gaps on purpose to get people to pay attention and to write notes in there if you want. If you want to, you can take notes on class. You can print those off ahead of time or download them, whatever you're going to do. Or if you prefer to just listen or take notes on something else, that's fine too. What I do is at the end of each section is I upload my notes that now have my scribbles on it. So you'll see class notes before versus after class, and other things there in the file section. Okay, in addition to Canvas, we'll be using one other resource, and that's Top Hat. In the past, I've used Turning Point. That's a clicker that you might have used elsewhere on campus. And I really tried to make it work, but I just found the software is far too buggy. The app didn't work. People would be showing me, they tried to put the answer in, and it wasn't working. So we're going to try something new this semester. We're going to use Top Hat. I like Top Hat because you don't have to buy a physical clicker. You can use your phone, you can use the browser on your computer. If you have a phone that's not a smartphone, you can actually text your answers in. I'm told that this is not a large fraction of students doing this, but it's an available option. And if none of those options are available, come talk to me and we'll work out some custom thing you can do. Okay? There shouldn't be an impediment to you in terms of the technology you have to be active in class. So how it works, Top Hat, you're seeing what is like the instructor view right now. When you guys are answering questions in class, it will look a little bit differently. But essentially what I have is I have a whole bunch of questions that I have for in class. I have reading questions, which are really easy questions if you've done the reading ahead of time. And in the past, I did that reading quiz at the beginning of class, but I learned that nothing sucks the air and the energy out of the room like starting class with a reading quiz. It's like, it's the worst. It's just the worst. And so I'm not going to do that this year. Instead, Top Hat lets me schedule. So I can say that 24 hours before class starts, whenever you want, with a buddy, with whoever you want, you can take that quiz. They'll be really easy. It's just to get you to do the reading. Because I find in the past when I say do the reading, people don't do it unless there's like some reason to do it. And we're actually going to give you like a timeline and a schedule. So if you fall behind, you can just get back on and like figure out where you're at. My TAs, we'll introduce in a moment. We'll show you how to do that. Another great thing about Top Hat that I really, really like is for each chapter that we're going to cover in the books, here's the chapters that we're going to cover. I've gone ahead and I've created what's called a discussion. I've already assigned this. So if you've already got your Top Hat subscription, which you're going to have to pay for, I apologize, it's like $26, but I think it's worth your time. Like, evidence is overwhelming that active learning improves your learning outcomes, so I do believe in it. I hope that the cheap book sort of offsets that. But for here, you can see in this discussion section that for each chapter I have worked example problems. Every year students say, I wish you had more examples, right? You go through so fast with the material, I wish we had more examples. So here's a great way to have that and have it be organized, right? When you pull this up, you'll see that, in chapter 2, you can see an example of interatomic forces. You can click this and it's an embedded YouTube video, and up will start playing a video that actually walks through a real life problem. You can click the title and go straight to YouTube if you want to see it in a different format. But that's available for all these chapters, so I think that that'll be a useful resource in addition to Canvas. Okay. That said, most of the time that I lecture will be out of OneNote. It'll be something like this. Let me introduce one quick thing here. Well, I'll get to it later. So let me introduce the TAs for this class. This is a great big class, and it's a hard class. And so we want to make sure that there are just so many resources that even though students come from lots of different lifestyles, you got like work, you got kids, you got no kids, you got living on campus, off campus, we want to make sure that there's a resource that can help you do well in this class. So let me introduce our 5 TAs. Can I have you guys stand up? So we've got 5 just cream of the crop, really, really awesome TAs. We've got Matt over there, Sarai, Logan, Danny, and Ashley. They're just phenomenal. And their 100% goal is to be your advocates in this class. So if I'm writing test questions that are too hard, I have my TAs take the tests first and they say, Sparks, knock it off. Like, this question has no business being on a test. And I try my best to listen. And they are really your best advocates. They oftentimes hold study sessions. The way that we've structured homework help and TA sections this semester is homeworks are always due on Wednesday, right? Class is Monday, Wednesday, Friday. Homeworks will be due on Wednesdays. And so in the past, we had one Tuesday night section, which was really helpful, but it was just slammed. They actually held it in this room, and it was so many students, it was hard to get all the help that I think we needed. So now we've tried to space it out a little bit. I assign the homework typically on Wednesday or Thursday. So for those of you who are smart, it'll start on Friday. We have some office hours to get you started. For those of you that put it off over the weekend, we front-loaded the beginning of the week with office hours. We tried to do a mix of morning and evening. And if these times don't work, anytime that my office door is open, you can pop by, and I'm delighted to help you out. And if you can't find that to work out either, then you can use the discussion section on Canvas. And we respond to that really quickly, right? We pride ourselves on being pretty good at responding to that. So that's our TAs. I've got their contact information here as well as where they're going to be holding their office hours. So again, they're your advocates. Get in touch with them. They're going to do a great job. Thanks, guys. Okay. I will always hold I'll hold a personal review session the week of a test. So tests are always on Fridays, the midterms. And typically on a Tuesday, Wednesday, or Thursday, I will hold a review session myself in the evening. And if you can't make it to those, don't worry, I screen cap those and post them on YouTube as well. Okay? All right, so there are some concerns that crop up every year. You've probably heard them from your peers, right? Here's the 3 most common concerns for this class. First one, some of the material that we cover is not in the textbook. For example, thermodynamics, we're going to have some additional readings in course notes. So should you be worried? Not at all, right? The second concern is some of us might have seen free energy or reaction equilibrium in the second semester of Gen Chem, and others haven't, right? For some, they've taken the second semester of Gen Chem, and some of you guys haven't, because it's not a prereq for this class. Don't worry. We're going to teach that in this class. We've got oodles of examples, so you don't need to be worried about that. And then the last one is we're going to go slightly out of order in the book, right? The reason we do that is because we've got civil engineers in here, and I want to make sure that since we're only here for the first half of the semester, that we get the most important stuff to them first. Things like fracture. I feel like civil engineers don't know about fracture. So we're going to talk about that, right? But that's chapter 9. So we had to move things around a little bit. But trust me, it'll be okay if we go a little bit out of order. Okay. I already talked about notes with gaps. Let me say a little bit more about the notes. The notes that I prepared are really, I read through the chapter and I said, ooh, that's good stuff, I'm going to teach that. But it's certainly not exhaustive. The textbook is more exhaustive than my notes. And so you'll be responsible for the stuff that we talk about in class, right? If it's in the textbook and I didn't cover it in class, it's not going to show up on a midterm, right? In fact, I have a very strict goal for myself that I will never put something on a midterm that you haven't seen on a homework, right? At least the concept. I might ask you to rework it in a different way. That's reasonable. That's applying what you've understood. But I will make sure that you've seen it on a homework first. So if you're seeing lots of stuff in the book and we don't get to it, great. That's stuff that you don't have to worry about studying. Okay. I've already mentioned that I screen capture these classes. You can follow the link. You can subscribe or just follow it each time if you want. But I'll be posting the lectures to this YouTube playlist. It should be embedded in the course notes if you want to download that. Okay, we're going to talk about Top Hat. Talked about labs, so a little more about labs. Labs will be held Tuesday or Thursday, those of you that are taking the labs. Those will be great. They'll be typically every week, although we do have weeks off, weeks of a test. We don't have to make you worry about doing a lab those weeks, and weeks of like fall and Thanksgiving break. You don't worry about labs those weeks either. They're going to be great. Many of you are going to have, no matter what you do actually, you're going to have to do technical writing of some sort if you're an engineer. And we're really trying to drill down this year and making sure that technical writing for these labs help prepare you for your career. So I hope we're going to do a good job on that. It's our goal to make that better than in years past. Okay, homeworks. I already said that they're challenging. You really do not want to wait till the night before on homeworks in this class. They're challenging, right? I give you some book problems that will at least teach you how to use the equations. But when I write test questions, well, first off, when you look at a homework, all the questions you see there are old test questions or something that I would consider the equivalent when I've written a new one. So, and they're challenging. You want to start early on those for sure. If you do buy a book that's not the 3rd edition, which is the official textbook, in the files section of Canvas, I've got, where is it? Right here. The scanned 3rd edition homework problems every year without fail. It happens, even though I announced this. Someone will buy the 4th edition and will do the book problems out of the 4th edition, and they're not the same. So if you do buy whatever other edition of the book that you wanted to get, you can pull up the homework problems to do right here. We've got them scanned in there. Yeah.
Can we just clarify that lab starts this week?
Yeah. So if you are a 2010 student, start this week. We're actually talking about lab safety and writing lab reports this week, even though you're not going to be making cool experiments in the lab per se. So you will be starting this week. So be there tomorrow, those that have Tuesday labs. To get the homework back to you, we used to pass it around in class. That's not allowed anymore. So you're going to have to actually pick it up from either my office or from the TAs during office hours. To make that easier to get it back to you, we will alphabetize the homeworks. And let's say that if there's going to be 10 homeworks over the course of the semester, we won't just put those all together. We'll bundle them together in rubber bands. But still, it gets hard for us to keep track of everything. So it's easy if you pick it up sooner, and there's less of it in this giant bin to dig through at the end of the semester. But it's up to you. You don't have to pick it up. But if you want to, it's in your interest. One of the reasons why it's in your interest is because we can't grade every single problem every week for all 150 students in here. So instead what we do is we pick select problems and grade them. We won't know which ones those are ahead of time, and we grade off of those. So if there's a total of, say, 15 questions, most of them we book, and then 3 test questions, we'll grade, I don't know, 4, 5, 6 of those. So be aware that we're not grading everything. So what that might mean is you could look at the score you got, and it was 10 out of 10. You're like, oh, fantastic. But it might be that we just didn't grade a problem that you actually did incorrectly. So I do post solutions. You definitely want to look at those. And I think it's a good idea to actually dig up your homework and make sure that you worked it correctly afterwards. Okay? Getting your name back to you. If you've got many last names, which some of you have, just circle the one that you want us to alphabetize it by. Okay? Circle that first letter. And we're happy to look at grade errors on tests and midterms. That happens, we're humans. We do our best to make sure that things are graded fairly and correctly. But if it is the case that there's a mistake, you can come to us and get a regrade. But we ask that you do it within a week? Within a week, because otherwise at the end of the semester, everyone's trying to get final points wherever they can, and we just can't go back and regrade things for the whole class at that time. So you got a week to basically ask us why you got the score you did. Okay, let me just say, I bring it up every year that cheating will not be tolerated. We will take great lengths to prevent cheating in this class. And when I first taught it, that was not the case, and there was more cheating. And I'm happy to say that we haven't had nearly as big a problem the last couple of years. We've really cracked down on it. So I'll just say, don't make me have that conversation with you. It sucks. We have to talk to the dean. We have to talk to the chair of your department. It's an uncomfortable conversation. So don't cheat. Instead, get the help you need before that you're in trouble on a test or something. So how do you do well in this class is another common question I'll get. The way to do well in this class is to do the reading, come to class, start the homeworks early, and if you ever don't get something, come talk to the TA. Like, you do those things and you'll be just fine in this class, right? Start the homeworks early, come to class, do the reading before class, and ask questions. Okay, who's taking this class? This is the breakdown, mostly mechanicals, and about a quarter of them are material students with a little bit of everything else. So what are we going to learn about, right? We've got another 30 minutes or so. What are we going to learn about in this class? What are our learning objectives? Well, here's the learning objectives that I can think of for all of you as engineers of all these different disciplines. I want you to know what the relationships are between the structure of materials, how we process those materials, and then the properties you get out of them. Those three things, that's like the heart of material science. Structure, property, processing, we call them relationships or linkages. And I have some neat examples of that. I want you to know what material to use in different instances. If you're designing a road, if you're designing an overpass, if you're designing a car that travels on that road, if you're just designing the glove box within that car, all these things might have very different materials that you choose to make it out of, right? And the goal in this class is to give you a big picture idea of what materials are out there and how do you down select to the one that's appropriate for a given application, right? I want you to understand the difference between amorphous or glassy materials and crystalline ones. We're going to talk a lot about crystalline materials. After we introduce the concept of crystalline materials, we'll describe defects. So when things aren't perfect, right? Because I can imagine like a perfect three-dimensional structure, but what if you got a messing atom? Well, what if one of those atoms just is crammed into the spot where it ought not be, right? What does that do to properties? We're going to talk about that, and actually it's very important on properties. Something that I've been passionate about myself as an engineer is sustainability. I think that engineers oftentimes we're only driven by the bottom line. That's all your boss, he or she may be only worrying about is the bottom line. I think that we should care a whole lot more about that, and actually the TAs have requested to teach that section this year, and they're going to do just a bang-up job on that. So I hope that we don't have a ton of time to spend on it. We will talk about sustainability, and I hope to weave it into the course throughout in terms of renewable energy, recycling, the broader impacts that technological development has on society. Something I'd also like to have you guys do is be able to predict materials' properties from a given composition, a structure, or an environment, right? So if you've got a metal at a certain temperature, I'd like you to understand, is this going to corrode or not? Is it going to be weak or not? Be strong? And the last thing, learning objective that I'd like to get across to you is how are you going to know what phases of matter are stable, and if not, how rapidly, what sort of time frame before they evolve to a different phase that's either better or worse than the one you started at, okay? So maybe before we get started and diving into these learning objectives, let's just start by examining what different classes of materials are out there. They're all around you. Literally, you can start pointing to different things around you, and you can see that different classes of materials absolutely surround us, right? And they sort of all have their strengths and weaknesses, right? It's not like there's one that's good for everything. They really are fit for different applications. Take polymers, right? Polymers in general, and again, this is general because there's exceptions to the rule, they're flexible, lightweight, and can be easily processed, right? If I just sum up some of the key things about plastics or polymers, that's what I'd say about them. But there's exceptions. Take Kevlar and that bulletproof vest. That stuff is certainly not very weak like many polymers are. It's not even very flexible. It's pretty rigid, right? That's why we use it. You've got other things that are not very processable at all, right? You've got styrofoam in this class. You've got elastomers, like rubber bands, right? A very, very different class of materials compared to anything else, right? Beyond polymers, you've got your ceramics, typically known for their high hardness values, high strength, their high melting points, and their brittle nature, right? These things fracture pretty easily. Any of you who've had like a dinner plate or a glass and you drop them, you know they break pretty easily. So you might not think that they're strong materials, but in fact they have high strength, but they have also as low toughness, right? So we'll talk about the difference of what do we mean by toughness versus strength, different things. The ceramics are an interesting class of materials. That's what I work mostly on, and I will tell you, when should you use ceramics? only if everything else fails. Like, they are miserable, horrible things. But sometimes they do the job. Like, for example, take this artificial knee or the artificial hip, right? Why would you put that? Let me just ask you guys, based on the value, what I told you, high strength, high hardness, high melting point, why on earth, maybe turn to a neighbor. By the way, I'll be saying that a lot this semester, because I want you guys to actually not just be listening, but to interact. Turn to a neighbor and say, why on earth is the inside of that hip, that's this guy over here, this thing, why is the in part of that, the pink part, why do you think they made that out of ceramic? So, Jacqueline Shelley, what do you think? I'm going to pick on Sam, and I know your names, most of them. So I printed your name sheets ahead of time and memorized them. So if I don't know them yet, we'll soon. Sam, why? What do you think?
It's a lot like bone.
Yeah, bone's already a ceramic, so replacing a ceramic with another, that's already a pretty good idea. All right, what else?
You said that we thought that maybe it's durable and it won't degrade over time.
Yeah. That's exactly right. Like, how many times, you don't even think about it. Like, now that we have step counters, we kind of keep track of this. Like, 10,000 steps in a day is like a normal day. 10,000 times that, like, that little ball and socket has to, like, slide past each other, right? What if it was a soft material, right? Then it's going to get, what if there's, like, a little bit of a bone spur, or, like, I don't know, crap, it's in your head. But if there's something in there and it, like, grinds into there, that's a problem, right? So they picked it exactly because it's durable. Its durability is the number one reason why they picked this. Now, why not a metal or a plastic? They pick a ceramic because it has a high hardness. Anybody want to venture to guess why hardness and durability are related, especially in this case? Any guesses? Hardness and durability. Because ceramics, we just said that they're brittle, which doesn't sound like something you want on your hip. But why do we do it? Yeah?
Because it doesn't deform.
It won't deform. That's really important, right? Every time I jump up and down, right, I'm loading it. I don't want that to get a permanent deformation, because then every time that I walk, it might rub or break, or I don't know that. That's a good one. What else? Why does hardness matter? What do you think?
Maybe lower friction.
It is lower friction. Why does hardness lead to lower friction? Exactly right. Any thoughts? Yeah.
It's not going to scratch or anything like that, so it'll stay smooth.
Yeah. Once it is smooth, it won't get not smooth, right? It won't get scratched. And actually, a hard material is one that you can polish to a higher smoothness to start with. That's not intuitive at first. But a material, if you have two materials, two types of steel, so one's harder than the other, the one that's harder will take a longer time to get it smooth, it's more challenging, but it gets to a much finer smoothness. And if you got a ball and socket, you definitely want that smooth, because then there's less wear, right? So you can see that even though ceramics are like a miserable class of materials, they have properties that make them useful for, well, at least one application. Right? They're okay, that's ceramics. Let's talk about metals. Metals, again, in general, are excellent conductors of both heat and electricity. And there's exceptions to that, right? There's metals that aren't very metallic in terms of electrical conductivity. There's ones that don't actually conduct heat that well, right? But most of the time they do those two things. They're typically ductile, that's not always the case, and they're generally fairly strong, but not as much as ceramics, right? But you can see exceptions to this. Like, we can process them in really interesting ways, right? This material in the top left is, to my knowledge, the lightest weight, lowest density structure that's ever been made. It was made at HRL, Hughes Research Lab in California. We'll talk maybe a little later about how they made that. You can make things that are shape memory alloys, like these stints up here. These stints, they start out collapsed. They go in some sort of blood vessel, right? And then at a certain temperature, your body's at a higher temperature than room temperature. After a certain period of time at that temperature, they automatically pop open, right? This shape memory alloy has an energetic driving force to do that when temperature changes, right? So they've got some interesting functional properties, metals do. They're easy to recycle, generally speaking, more so than some of the others. So they have some advantages for them. There's also semiconductors, right? We can talk about semiconductors. These things, we all carry extremely advanced semiconductors in our pocket without even giving it any thought. but semiconductors are devices that make possible things like LEDs, like integrated circuits, like transistors, lasers, photovoltaics, on and on and on. Semiconductors are an interesting class of materials because they sort of lie in between ceramics and metals. In terms of properties, both mechanical, electrical, they're sort of in between those two different classes. And we'll get to some of those more details later this semester. And the last class is really just mixtures of the other classes that we've described up until now. Composites. Composites take advantage of the strengths of two different classes of material to get an overall engineering product which has some of the best of both. Has the weaknesses of both, but the strengths of both, right? So take like glass fiber, right? Fiberglass, you've seen that before. We make boats and stuff out of it. Why do you think, turn to a neighbor and discuss, why do you think we make a boat out of fiberglass as opposed to just epoxy or just glass? Because that's what it's made of, epoxy and glass fibers. So turn to a neighbor and discuss. Okay, what are your thoughts? Why on earth are we combining glass and epoxy to make airplanes nowadays instead of just good old-fashioned aluminum that we use for decades, right? What benefit is there? What do you guys think? Airplanes or boats or whatever it may be. What do you think, Jack?
It's light.
It's light. It's lighter weight than a lot of metals, right? Does that matter for transportation? Yeah, you betcha, right? Already, quick question. You guys realize how efficient your cars are? A car, right? What would you guess fraction of energy actually moves you forward of a gallon of gasoline? 30%? That's a darn good guess. It depends on your vehicle is the real answer, right? 30 is pretty close. It's about 20% on average, right? So and a lot of that is just moving this hunk of metal or whatever forward, right? So the lighter you make it, the more fuel efficient your vehicle is going to be, right? What else? So density is a big one. Probably the biggest reason that they do many composites is just to get the density down. But what else? Are there other benefits? Yeah, we think, right?
Very strong.
Yeah, we just finished saying that these fibers, these are glass fibers or carbon fibers, those are going to typically be high strength, right? So you can actually get an overall increase in strength of your material. Now, is that always going to be the case? What do we have to take into account here? Kind of two main things. When you pull on it this way versus transverse to that, you can expect very different properties, right? In one case, you're loading along the fiber axes, right? So you're gonna have one set of properties. In the other one, the fiber's not really doing you much good. All the load might be carried by the what we call the matrix phase, right? And that might not be very good at all, right? Okay? We could go on and on, right? How, if you do make, let's say you make a carbon fiber, like a panel like that, how do you join these things? That's like that's an important area of composites is, okay, you made the thing, how do you join it to the rest of the components in your overall device? That is often the most challenging part of composites. Okay, so that's material science. But what else is material science? Is food material science? Is chocolate material science? Clearly it is. I prepared a demo, right? If you want to learn more about it, that link there takes you to a fascinating talk from a guy from Barcelona who talks about, for like hours on end, about the science of chocolate. I'm going to not do that. I will do something that I think is neat. So over the weekend, this is like, it makes me a little bit sad that I do it every year because it means summer's over, but the week before class, I cast chocolate in preparation for this class. And I do so and see the following, right? So let me get my computer. Maybe I'll try and take a picture of these. Oh no, I've got some, never mind. So mine looks similar to what you're gonna see on the screen, right? Every year I cast it, and you might have seen this before, right? If you left like a candy bar in the car or something, it started out nice and like that dark color, and after a while, it looks like it's got that mold on it. So it's not mold. That's actually what's called chocolate bloom. Chocolate is made of what? What is chocolate? It's sugar and fat. It's cocoa butter, right? It's a type of fat. So it's basically two phases, right? That means depending on what you put in it, right? And what happens is that under certain conditions, those two components separate from one another, right? So there's a structure where they stay together. That looks like the chocolate you want to eat. And there's a structure where they don't stay together. They phase separate, and that looks horrible, right? It's the same thing. It's the same component. That's not mold, right? And so what I do is every year I cast it 2 different ways, right? Here's our Lego men, right? We cast these. We're scientists, right? We just experiment ourselves. And the top one is what's called tempered chocolate. Those 4 on top, and the bottom ones are untempered, right? And at first glance, these guys look okay, right? Untempered chocolate looks pretty good. In fact, these ones look a little bit funny. See, like the smooshed face. That's I had water on my fingers, so I messed that up. Right? So ignore that. But after even a day later, and certainly after a week later, they look like this, right? Your Lego men look like they have leprosy, right? They look like it's not good at all. And you can actually see this. There's a sweet time-lapse video we'll show you. So check this out. So here's our friend from Barcelona talking about what I was describing in a moment. And then he shows the chocolate that they cast in a tempered versus an untempered state. And if you look at it, this is a time-lapse. Very clear separation of the sugar from the fat, right? Which just is not appealing to eat at all, right? So we need 4 brave souls. Actually, we could do a bunch of brave souls. Who's brave? Come on down. Come on down. Is it Colby? And I didn't catch your name. Right? Josh. Josh and Colby. Who else? 2 more at least. In the way back. And right here. Come on down. I don't know your name. Adam and Jordan. Okay, so you guys are going to try some chocolates for us. So first off, try the untempered chocolate. Right? I promise these are all like Ghirardelli. Like they were nice chocolates to start with before I cast them in an untempered state. And thoughts on the untempered milk chocolate. By the way, I used to do this with dark chocolate, but I've discovered that millennials are heathens and they don't like dark chocolate. I don't understand you people, but I will accommodate bring milk chocolate nonetheless. What do you think?
Chalky.
Chalky is the perfect word for it. The texture's not right. Once they mash it a little bit, it's still milk chocolate, right? The flavor's about right, but the texture is just awful. Now, take that one and try and snap it for us. There's no snap. It just crumbles, right? Usually we have a nice microphone, and I take one of these things and like, it's got a snap. This stuff's nice. This stuff has no snap at all. All right, now try one of these. The same exact batch. Grab something. I'm going to send it around. If you want the untempered stuff, you can jump into the battle. Okay, what are your thoughts?
It's better.
It tastes more normal, right?
Smoother.
Smoother.
The initial crunch is great.
Right? Okay, thanks you guys. Thank you so much. So what did I do differently, right? What was the difference between these different chocolates? Here's the key. And this is how it ties into material science, right? Chocolate is a mixture of 2 components. Tons of the things that we're going to work on this semester are a mixture of multiple components. If it's steel, then that's iron and carbon, right? So when you mix these components together, they might be in a single phase, or they might be in 2 phases where they phase separate. For chocolate, you want a single phase. Now, when you heat chocolate up, there's actually 6 different ways that chocolate can arrange itself together, right? You can imagine like for every like fat molecule, you got like a sugar next to it and a fat and sugar, like an alternating pattern like that. So that's like the beginnings of what we're going to be talking about this semester as crystal structure. It's more complicated than that. But think of it right now as just ways of arranging these things together. And it turns out, when you cast chocolate, so you heat it above, what's this one? Above, say, 36 degrees Celsius, because we're not barbarians, right? You heat it above there and it's a liquid. If you cast it, what it's probably going to form in is one of these phases down here, right? And these first 4 phases, while initially they're single phase, they're what we call a metastable phase. Metastable means what? Metastable means it's not really stable. It's unstable, right? It's temporary. A little bit of energy fluctuations and it's going to switch to something more stable. And that more stable phase is the 2 separating, and that's not what you want. So instead, tempering chocolate, all you have to do is you heat it up to melting, right? But before you cast it into your mold, you cool it down in that narrow, and we're talking a couple of degrees difference, right? In this case, between 32 and 36 degrees. Either of those top 2 phases are stable, right? So you hold it there. It starts to thicken, right? It makes it harder to cast. It's not as runny and liquidy. So that's why my things aren't as like lovely looking, because it's a little bit thicker to cast. you put them that way, then they remain stable. Other things you could do is you could cast it in the totally liquid phase and then put the whole entire mold in an oven and hold it at that temperature. There's other things you can do. You can take seed crystals, so take that really nice Ghirardelli chocolate that you had just melted, but save some of it, and when it's ready to be cast, cool it down by adding chunks of the stuff that's already in the right crystalline phase, because Ghirardelli definitely knows what they're doing, and add that in, and those will grow, like just like seeds grow, it'll grow into big phases of the right crystal structure. So even something as benign, that's all around us like chocolate, right, the food that we eat is actually subject to quite a bit of interesting engineering, right? In this class, we're going to be understanding how aluminum, steel, plastics, rubber bands, all these things, they all have properties you want to get out of them, and understanding how the structure relates to those properties and how processing gets you to that structure, that's this course. That's material science. Okay? Okay, 15 minutes left. Let's go ahead and dive right into the first chapter, right? We got 15 minutes left. So what are our learning objectives for today? Something I'll try and do every day when I lecture, tell you what do I think the objectives are. And today, my objective is to help describe how atoms exist in terms of electronic orbitals. This is stuff you've seen in chemistry. I'm calling this like chemistry and fast forward. I'm just hitting the highlights so you remember them. I'd like to be able to calculate between energy and wavelength of light. As electrons hop between different orbitals, that's different than energy. So it's going to give off light. We're going to figure out how to calculate those things. And we'll tie that into EDS, a really powerful engineering tool. We'll learn how to write out electron configurations, and if we have time, we're going to talk about interatomic forces. So if you've got two different atoms, say sodium and chlorine, that makes up salt, sodium chloride, how do those things interact with one another, especially as you bring them close together or further apart from one another. We're going to sketch the interatomic force and therefore the energy. Okay? So let's start with chemistry and fast forward. Chemistry answers, I think, one of the... if you didn't love chemistry, let me make an appeal for you to love it after this semester, right? Because I hope that if you didn't love it, it's because you didn't see the applications of it. And engineering, particularly material science engineering, it's applications of the chemistry principles towards problems that you might actually care about, right? And it answers all sorts of questions, right? Why are some solids soluble in water, like salt, but other ones like sand not, right? Chemistry explains this, right? Why do some things melt at a high temperature versus low? Why do things like noble gases exist, and why are they gases instead of solids, right? All this can be explained by understanding the principal thing is bonding. But before we get to bonding, we have to go back to the structure of an atom, right? So, structure of an atom, we're going back to the turn of the century, right? We've got Robert Millikan and J.J. Thomson, right? J.J. Thomson figures out that there's these things called electrons, and they've got a charge. He knows that because he puts them in an evacuated tube, he applies a voltage across it, he starts bombarding it from one end of the tube to the other, and when he puts this plate in the middle of that path and puts a charge on it, they drift up or they drift down. So he says, aha, I'm adding positive or negative charge to this plate and I can make it move. Therefore, they must be interacting electrostatically with that, right? So we know that electrons exist and they've got a charge. Next comes Millikan, and he figures out the mass of an electron in a way that just boggles my mind. You probably saw this in physics, the oil drop experiment. Follow this with me. This is amazing. He literally took like a sprayer, right? Like he misted oil into this thing. In that cavity, gravity's acting on the oil drop, so it's falling downward. And then he applied an electric field the other way. So if these things are charged with electrons that have a negative charge, if you apply a field the other way, you could feasibly pick a voltage where the upward force of the electrostatic repulsion matches the gravitational force of falling. And that's how he figured out, based on the size of the droplets, he had a little microscope, he saw the size of the droplets, he figured out what the charge of an electron must be, as well as the mass. Just mind-boggling that actually worked. That seems like crazy. If my student proposed that to me in my lab, I'd be like, sure, that's not going to work. Don't do that. And it worked. And it was a Nobel Prize, right? By the way, while we're on the subject of Millikan here for a minute, Robert Millikan, he wasn't even an engineer. He wasn't a physicist. He was a classicist. What's that? It means he studied Greek and Latin. That was his thing, like Princeton or Yale or someone, right? And they needed somebody to teach their physics course, Newtonian mechanics, right? He was not a physics person. He didn't ever take any courses, but he said, I need a job. I'll do it, sure. And so this is what he said. I doubt if I have ever taught better in my life than my first course of physics in 1889. I was so intensely interested in keeping my knowledge ahead of that of the class that they might have caught some of my interest and enthusiasm. Can I say that that's still me 6 years later after teaching this class? I still get questions from you guys where I'm like, I don't know the answer to that. But I hope that some enthusiasm and interest will bleed over, even if you're not a material science student, I don't care. Like, I hope that this class will be worth your tuition money, that you'll have some interest in these things that we're learning about, and it won't just be to check off a box. If it's to check off a box, that's okay too. Okay, so we know that electrons exist. We don't know about neutrons, nuclei though, right? Here's the Rutherford experiment. They take particles, pretty big particles, right? It's like alpha radiation or something. Yeah, it's alpha particles. And they have a very thin sheet of foil with this illuminating detecting screen around the outside, and they shoot it through the foil. And they expect it all to just go straight through. And all of a sudden, some of it bounces back. When you read what he said about this, he basically described it like, it's as shocking as you held it like a piece of tissue paper, like a Kleenex, and shot it with like a giant battleship cannon and saw it bounce back. Like, that's how shocked they were. That some of these would bounce back, they just could not understand. And what they realized, there must be something in here. There must be a dense but very small core that electrons or particles, when they hit, will bounce back from. And all of a sudden we know that there must be a nuclei, right? So it's not our beloved plum pudding model where positive charge is just sort of everywhere with electrons like raisins in the plum pudding. Instead, electrons we know are occupy a certain volume, but there's a core which is positively charged. Okay? Okay, let's move to Geiger, Marsden, and Rutherford. Oh, that was them, sorry. Now we move to Rydberg and Bohr. So we know that electrons exist, but are they this nebulous cloud just floating somewhere around the nucleus? Or do they sit in certain spots, right? So Rydberg realized that they actually sit in certain spots. And how he figured this out is he took different metals and he burnt them. And when he burnt them, he basically had a prism. And if you've seen like Pink Floyd album, you know that light comes in and it splits, right? So Rydberg's doing Pink Floyd stuff in 1888, and he realized that different elements split in different ways. And he says, how can this be? Why is different? First off, why is it discrete? It's not this band, because when you see metal burning, it's a bright white band, look at it, right? So why is it when you split that up that there's certain discrete levels, and why do they depend on what metal you're burning, right? Confusing stuff. So Niels Bohr comes along a little later. All these people are Nobel Prize winners, right? What they did. And he said there must be discrete energy states that your electrons occupy, and they must be able to move between these states. And since energy is neither created nor destroyed, but just converted from one form to another, that difference in energy manifests itself as radiation or light, electromagnetic radiation coming off these things, which has a different wavelength depending on the energy gap between these different things, right? And this brings us to the first amazing material science tool that I hope to teach you about. It's called EDS, Energy Dispersive Spectroscopy. It's going to be on the first homework for sure. It'll be on the midterm probably. EDS, Energy Dispersive Spectroscopy. Here's how it works. If you're working in a lab somewhere for Intel or for Black Diamond or for whoever else, let's say your competitor makes a newer, better gizmo than yours, and your boss says, this will not stand. Figure out what they did so we can do it better. And they hand you the thing, right? One of the very first things that you're going to do is chop it up into pieces and look at what the structure is. Okay, there's some metal over here, there's some plastic, but metals all kind of look like metals. How do I know which one it is? And maybe like your metal's got a bunch of different phases, right? When you look at a microscope at different regions that clearly look like they're different, how are you going to figure out what's there? EDS is a great tool for this. Here's how it works. If you guys are all electrons moving outwards to higher energy values, and this is the nucleus over here, think of electrons as people that go to the theater that really want to be at the front row, right? So there's an empty seat here. So Hunter's like, oh, damn, what am I doing on row 2 when I can just move forward to row 1? Like, it's so much better in every way. So keep going. Hunter, come on over here. What are you waiting for? So he moves down in energy, and in doing so, he's going to have to do what? And you can't just destroy energy. What do you do with your energy? Yeah, that's what we're doing. Beautiful. Yeah, he gives off a characteristic, a fingerprint radiation level, right? And you know, that was because it went from what's called just energy level 2 to 1. And these have specific names depending on which orbital we're moving around from. That's the idea. So for example, Chantal. If she moved down, it would have given a different energy. We don't see. Come over there, Chantal. Please. So that's going to give off a different energy level than Hunter gave off. So all you need to do EDS is you need two things. You need a way to create empty seats And then you need a way to measure the radiation that comes off. Now it's like full, right? So what do? We can't use this tool anymore. All our innermost energy levels are full. What do? What's that? You can fill up row 2 because we emptied those seats. Let's just say that everything was all down as low as it could go. It's a good concept. People want to be in the front row. Like, there's no empty seats. Right in the back, it was at
Maybe I'll go further back.
remind me your name again?
Jordan.
They might go further back. Nope, things won't go up in energy unless you make them. But what else can we do? What can we do? What if we could kick somebody out? We can kick somebody out. Ryan, did I ask you to go back a row? So Ryan's going to move back. How do we do this in metals and atoms and whatever? We take an electron gun. They actually call it an electron gun, right? It's a beam of electrons. We bombard this thing, and some fraction of those electrons will hit an innermost electron and bump him somewhere else. He'll take that energy and say, I've got less energy. I'm going to go to a higher energy level, right? And there he goes. And now it leaves an empty seat. Meanwhile, Elias is going to say, there's an empty seat. He's going to move over. You know, listen to him. Then you can't. Right? So that's how EDS works. It's that simple, right? So when I talk about different types of radiation, there's K alpha transitions, K alpha 1, K alpha 2, L alpha. All that is, it's just fancy lingo for which energy levels hopping from where to where, right? Like, these are our quantum numbers. We're going to talk about this in a minute. N equals 1, 2, 3, 4, right? We know that N equals 1, there's only 2 electrons. They got rid of our periodic table here. Where's that? Use that one, right? We can use that one. Anyways, hydrogen and helium occupy these sites, then it goes lithium, beryllium, and so forth, right? So if it moves from 3 to 1, that's going to have a specific terminology or name. If it goes from 2 to 1 or 3 to 2, all those have specific names, but don't get hung up on that. The principle is the same, right? It's just transitions and preserving energy. Okay. Other things that we can learn about. Let's see, we have time, yeah. Other things we learn about the periodic table and from chemistry is that there's trends that exist in the periodic table, right? For example, there's something called ionization energy. Ionization energy is different than EDS. EDS, we took an electron gun and we bombard it and we hit somebody like Ryan, send it flying to a higher energy level. That's not how ionization works. Ionization energy is kind of like a vacuum, right? Imagine that somebody had a giant shop vac in the back of this room, they hooked it to the door, and the outermost people are going to go flying off first. That's ionization energy, right? But how much pressure of air sucking out of this room is required before somebody goes flying out? In an electron speak, we would say how much voltage is required before you strip off an electron, right? Ionization energy. So which one's going to be held more tightly? So turn to a neighbor if you remember this from chemistry. How does the trend work? And it's probably written. General idea is something about ionization energy. What do they do? Anybody remember? In general, right? So this is ionization energy as a function of atomic number. So as a function of atomic number, first off, two, like it's up, right? Put these like regions, right? We now understand that these are shells. We'll talk about shells probably next time, realistically. But across a shell, they tend to get harder to pull off. The first one is really easy to pull off. The first one in that shell is always the easiest to pull off. Why do you think that is? What's always easiest to pull off the first one, but it's really hard to pull off the very last one? Something like argon doesn't want to lose its electron. Why is that again? Yes, it is farther from the positive nucleus. So yeah, for one thing, the further out it goes, well, that would go the other way though, because these are negatively charged. Positive nucleus, the closer they are, that should be even better, right? So this is harder, well, not easier. So what's going on? It's harder to pull off. What do you think?
Is it filled?
This shell fills up, and when it's totally filled, this is like the first bit of quantum mechanics we won't teach you why this is the case, but I'll tell you that electron shells like to be filled, empty, or half filled. We can see evidence of that. take like these guys in the middle, when they're half filled, there's like a slight energy bonus, right? And then when you're taking away that window to make it not half filled anymore, it doesn't like that anymore. You can see those right in the middle, evidence of the half filling, right? So when it's a filled shell, it's in a happy state. It's in a lower, when we say happy, I mean lower energy. I say energy, I'm talking about Gibbs free energy, and we'll get to that in a few minutes, right? So that's ionization energy. So this was another clear evidence that there's some trend here, like bands, if you will, or shells are forming that change the properties of materials. Okay, we're out of time, so we'll pick up here with the Rydberg formula next time.